Thank you. I'm describing the work I'm done with Ethan Yu Chan, who's sitting here, and Hong Nan Lu, who's on back home vacation in Vietnam. So, uh, so what I'm trying to address is the question is the fate of our universe. So there's many speculations, but the simplest one and probably most likely one is based on the value of the cosmological constant. The value can be positive, negative, or zero. If it's positive or zero, then the universe probably will expand forever. But if it's negative, then what happened is that the cosmic scale factor, I mean, the size of the universe is going to collapse into a crunch, and that's the end of our universe. And that will happen in finite time, and that means that there's a lifespan. Now, March this year, a few months ago, there's new results coming from observations, and those observations I explained strongly suggest the second option. And based on that, we can estimate the lifespan of our universe, and our gut number is like 33 billion years old, billions long, okay? So that's the result we try at. So first I'm gonna do is, I know this is not a cosmology conference, many of you are not cosmologists, so I'm gonna basically review the introductory cosmology, and then I'm gonna explain the data before this year, and then I will review the data that come out this year, okay? And how impact on our thinking. So that's roughly the outline what we have. So cosmology, very basic. Everything to take is by the Hubble parameter, which is the change of scale of the cosmic scale factor. And the equation is h squared is equals to density over a to the power 3 times 1 plus Wi. Wi is the pressure over energy density, the ratio, okay? So the simplest one is W is 0 for dust, for matter. And in that case, this term will go rho over A cubed, which is very obvious, okay? If the volume goes increased by a factor of 8, that means A increased a factor of 2, then the density will go down by a factor of 8, okay? So that's what matter, easy to understand. And radiation, W equals to 1/3, which means it will go down like 8 to the 4th. Cosmological constant, W is -1. Okay. That's very unusual, but that's what general relativity tells us, which means there's negative pressure. And in that case, what happens is you plug -1 into it, then that means that there's no dependence on A. So that is the Hubble parameter, which means A dot changes, the cosmological constant term will not change. The matter density goes 1 over A cubed. Okay. For the moment, we ignore radiation, okay, because today radiation is very small. So h squared, and also I absorb this constant into this to make it dimensionless. So omega are dimensionless also. So this is the matter density. This will be the cosmological constant, or we don't know what it is with dark energy. Okay, so this is the relationship we have today. And it's normalized in a way such that today A is 1, the cosmic scale factor we define to be 1. And then the H Hubble parameters is today's value, and this equation reduced to this when A equals 1. Okay, so this is the very simple equation, matter density and dark energy density. Now, matter, I include two things, both the ordinary matter, the baryon matter, and the dark matter that we know would be there, okay? So now, next thing is I say, what about data come in? How data come into, okay? Here, plot the curve. There are 3 sets of data which is relevant here. The other one which are important but less relevant, which I won't discuss. So first is cosmic microwave background. Everybody have the fluctuation of the 3-degree black body radiation that permeates our universe, and how it fluctuates. It tells a lot of information. And that's roughly coming from z equals 10 to the cube, which means about the universe is 380,000 years old. So that's what it is. The second one is supernova, which type 1a supernova, where luminosity is well defined. So from that, we can use how the distance is, the redshift. And that goes from z is 0 to 1, which quite recent. And then, in fact, that's how the first discovered the accelerated universe that they know that's dark energy. Okay? And the third one is acoustic oscillation of the baryons, and they call BAO. This is a little bit harder to explain. It's really very much like the photons free stream during interaction after electron and positron combine to atoms for neutral. And the baryons, same thing. But then as they move out, the dark matter density which clump them together, so the gravitational force. So that causes some oscillation, and that oscillation is supposed to be measured. And that's mostly located around z equals 0.4, which means that the universe is about 8 billion years old, roughly, okay? 10 billion years old. So this is the plot. We want to know how much is the matter and how much is the dark energy, okay? And you can see the following. The CMB data is like this, the supernova data this, and the BAO data like this. And they sort of intersect. That tells you that dark energy is roughly 0.7, and matter is about 0.3. Okay? And if the universe is flat, then this is line. So we probably believe that flat is the result of inflation. And so a lot of time people just assume it's flat. Now, I go this plot a little bit more reporting, putting them together. And this is known as the standard lambda CDM model. The lambda CDM model is the standard model in cosmology, very much like standard model in particle physics, okay? People, when you say standard model, they refer to the lambda CDM model. And what lambda CDM model does is the following. Dark energy, we don't know how it behaves. So we write the dark energy into 1 plus W3 power, okay? And if W is minus 1, then this is just cosmological constant, no change. But W may not be minus 1. The whole talk I'm going is W may not be minus 1, okay? So, but if W is minus 1, then it's easy. These plots, I repeated earlier, but show you where the dark energy cosmological constant is over 0.72, and the matter is 0.28. And about that, maybe 4 or 5% is baryon, ordinary matter. Okay? And from this, they can get the age of the universe, which is 13.8 billion years. So you must have seen this number a long time. That give us idea that we have very good idea about the age of the universe. Okay, and here's the basic assumption is W is minus 1. Okay, so this is no A dependence. Okay, but now people want to know more. So this is another way to plot about what happened if dark energy is minus 1. So 380,000 years ago, matter dominates, dark matter plus atoms, and then radiation there. Okay? But remember, the radiation dropped by 1/8 to the 4th, and dark matter and atoms drop 1/8 to the cube. So they're all going to drop. But dark energy, if the equation stays minus 1, if it doesn't drop, that means today dark energy dominates. So this is how evolution goes, and you can track down the dark energy to 72% if W is minus 1. And now, so the whole thing that the community in astronomy, one big thing is to measure W, okay? And so here it's plotted a different way, W. I plot the same thing. This is 15, 16 years old, and the data is still W map without Planck. And this is the region that's allowed by data. You can see all three intersect about region. And it's roughly -1. And remember, -1 means that it's cosmological constant. The density does not drop, does not change as universe expands. So the goal now is to measure this more accurately to find if really W is -1 or some other value. Okay? And the way to do is to measure BAO, measure more supernova, and improve the CMB data. So it's clearly, if you improve all three data, hopefully you will isolate more the point that they intersect, and that's where the W value will be dictated. Okay, that's the picture we have started. So March this year, two reports that W of the dark energy may not be -1. Okay. I mean, both are reported in New York Times and other journal, media, and they're called dark energy survey, DES, or dark energy spectroscopic instrument, DESI. So I'll call DES, DESI. So the DES is a telescope in southern hemisphere in Atacama Plateau in Chile. And what they do is they measure 60 million galaxies. Okay, it's a huge effort they've been doing for a long time, and 1,000 supernovas, type 1a. Now, DESI is the observatory in Kitt Peak National Observatory in Arizona, and what they do is same thing, but one is northern hemisphere, one is southern hemisphere. So together, they really cover the whole patch of sky, and now there are probably 30 million galaxies been measured, and the separation distance, clustering of the galaxies will dictate the BAO and the supernova data. And then what they discovered is that the cosmic acceleration driven by dark energy that began earlier time is slowly weakened now. So it's no longer -1, but it's slightly bigger than -1. Means the absolute value is a little bit smaller than 1. So this is the observation they made in March. So this is a little bit hard to explain, so I will skip that, roughly how the data plotted. So I just showed this curve for give you some idea the accuracy of data, so you can judge for yourself how you like to accept it or not, okay? So this is W, but W is not constant. It's a function of Z, redshift, which means how far distance scale from us, okay? And when Z equals 0, it's next door, okay? The Z higher means further away, okay? And when Z is 0.4, then it's away, but roughly 10 billion years ago, where we see it, okay? And look at the data, okay? Very big error bars. And yet, around here, when Z is about 0.5, 0.4, it's a little bit above -1. Okay. The message I want to get to you is that Z around 0.4, which relatively close, is less than -1. Absolute value is less than 1. While Z higher up, huge error bars, okay? Now, you combine this data together, DES and DESI, the claim is that the discrepancy between data and W equals -1 reaches 4.2 sigma level, which it means that the probability that this is a fluke is 1 part in 50,000. So that's a relatively strong claim, but it's not ironclad, because ironclad people want 5 sigma. Okay? But it's much better than 3 sigma. So what we want to do now next is to explain this. Okay, use a very simple model. And the model is, let's take the simplest case, is a simple Axion field with a simple term. We can make it more involved later, okay? So it's an Axion-like particle with a very small mass. The mass is 10 to the minus 32 eV. So very, very ultralight Axion particle. And with a potential this way of simplified version, and then evolve, okay? So how does it evolve? Well, the particle would be away from the minimum, And because inflation, everywhere we have same value. And if the Hubble value parameter is bigger than m, this term, damn it, so this doesn't work, it will stay constant. So it's behaved like cosmological constant. The energy density don't change. Okay, so it's like dark energy cosmological constant. However, when the Hubble parameter decreases, get to m's smaller than the mass, then it starts falling off. Okay, smaller falling off. The exact equation and it's the approximate very clear. And this fall off means that it behaves like matter. Okay, remember matter is 1 over a cubed. So this small model will sort of explain what happened if it's behave like dark energy or cosmological constant, and then you'll behave like matter. Okay, and that will one way to explain it later. And this have been proposed by over 20 papers. I don't know how many I lost count in the last 20 years. Okay, that means if dark energy varies, then this seems to be the simplest model. So what we did, a little different, is that we add the cosmological constant to it. Because what people used to do is to replace the cosmological constant by this Axion field. And what we decided is we keep the Axion field together with the cosmological constant. Okay? So that's what we end up. So it's a very simple issue. And then what happened now? Now H now has 3 terms, dark energy has 2 terms. One is cosmological constant, the other one's coming from Axion field, plus the dark matter plus ordinary matter, 3 terms. Okay? And this will stay constant, okay, remember? And this one will change in a way that we want to see how it changes. Okay, it will go with equation state -1, decrease to 0. That means from behave like cosmological constant and then behave like matter. Okay, that's the behavior it is. And then we can go ahead and see how we can compare this with data. Okay, and then fix the behavior of these two. So this is roughly the picture what happened. It stays constant, goes down. But we know that today, around here today, that the dark energy contribute 0.7. So we want, no matter what happened around today, it should be 0.7. Okay, so, and then you can vary the other parameters. So this is roughly the overall picture. So I'm not going to bother you with detail. It's that you go through the analysis, you try to find maximum likelihood, what it is, and then you change the parameters to lambda, omega lambda, the cosmological constant term, omega phi, the Axion field contribution, and omega m, the matter, target dark matter, Hubble parameter, and then various things. So you do the analysis to see what it is. Okay, and don't go through that. Crucially is the following: is that we divide into omega lambda positive and negative. Remember, omega lambda is just rescaling the lambda, okay? Not anymore. So we treat the distribution this way for negative lambda, blue. It's very many possibilities you can fit the data. And the red one, there's only one. And this is essentially the original model where omega is -1. That means the original model of lambda CDM where W omega W is -1 is still not ruled out by the data. Okay, very unlikely, but not ruled out. But lambda's negative is clearly dominant. Okay, so that's our result. And recently, another paper come out claims that probability of negative lambda is 93.8%. And we treat this as probability. This is posterior distribution. But if we treat this as probability distribution, then what happened is that it's roughly comparable to this number. Okay. So the statement we want to make is that as far as we can tell, the best fit to the Axion dark energy model is that the cosmological constant is negative. Now, what does the observation groups that see and DES do? Well, they actually like to fit a model which is called CPL model. Okay? This is the standard fitting formula they use for the last 20 so years. Okay? So W equals to W0 plus WA, 1 minus A. The DA model takes a little form, this form, okay? -1 times this, okay? So this W1 is positive. So this is different from this. First, the behavior is different, but you wrote the data. The shaded blue region is where the data are allowed. Earlier, I showed you the data where in this region, the error bar is huge, okay? And then the error bar gets small. And it turned out the really important is that this region where the error bar is small, okay? So let me take the first one. First one is the equation of state W is minus 1.5. And in the Axion dark energy model, it cannot be less than -1. Okay, so this is crucial. The two models differ a lot in this region, but as I show you, the error bar in this region is huge, cut off the whole range. So either one is fine. What really become a little bit different is in this region, okay? But you have enough parameter. They both do a good fit in that region, okay? So either model is fine as far as fitting the data go. But the thing is that this model require phantom crossing, which means that there's no credible quantum field theory model that we know which can generate this formula. And this formula is simply a light axion field plus cosmology generators. So that's why we take this seriously, okay? In fact, at the moment, there's no credible model besides this model can fit the data. So this is so far the summary. And then here we give the best fit value, okay? So it's not so but the key is that the cosmological constant is negative means that we really live in anti-de Sitter space, okay? Which is what drives the remaining of the physics. So what's going on is the following, is that omega phi plus omega lambda is 0.72. Well, if you different fit, it may differ by 1% or 2%, but roughly speaking is that. So in the original lambda CDM model, it's all in lambda, no axion. Now, when we turn on axion, we can increase omega phi, give it some energy, and then of course, lambda will go down because the sum has to be 0.72. The remaining 0.28 is in the matter. Now, if you put all of it in the axion field, then omega phi is 0.72. This is today's value. But if you find it increase more on axion energy, then lambda become negative. Okay, this is the key. And this is the best fit value we have. That means, so it's a little bit like you have a account with your money in it, and then you spend it, and if you overspend, then your account becomes negative, okay? And once your account is negative, there's consequences, okay? If account is positive in this region, then you can live forever, okay? So this is the message. The consequences means that the lifespan is finite. Okay. Huh? Isn't too bad. Okay, so question now is that how good is the data? I mean, even the authors of the paper, the two collaborations, each collaboration involved hundreds of people, and believe that data is pretty solid, very solid, but not ironclad. However, there'll be more data coming. The DAISY group will continue to run for another year, and then other telescopes coming, okay, including the Zwicky Transit Facility, Euclid, and I think NASA has a mission. And then what's interesting is that the Vera Rubin Observatory in Chile is running. It just started running a couple months ago, I think. Okay, so it's really running, and then that will collect a lot of data, and then other ones will come in. So in a relatively near future, in the next few years, there will be tremendous amount of data collected, and we will really settle this issue more clearly. Okay. So now we look at the future. Okay, what's the future? So we can rewrite the whole page is that the prime is the derivative with respect to time. Okay, I'll skip this formula, but keep the top one. This normalized the Hubble parameter, and time dependence is omega lambda minus h squared. So we plot three choices. The blue, the dashed line, lambda equals 0, and lambda is negative. Okay. So if the lambda is positive, then what happens is that you go this way. The h prime will decrease to 0. That means you no longer evolve and stay a constant, and then universe just expand exponentially. Okay, this is what we know, like inflation. So this is stable point. If the lambda is 0, then you also get to 0 when h go to 0 also, and you very slowly go to here, and then universe will expand slower, but still whatever. But it's negative. What happened is that as universe evolve, when Hubble h go to 0, and then become negative because h prime is not 0. Okay, so that means the universe now would have a positive Hubble parameter become a negative Hubble parameter. So we can now approximate this. Remember when we say the Axion field will constant and then becomes dark matter drop down 1 over AQ. So let's assume it drop down 1 over AQ. Okay, then you find out that the matter now is baryon matter plus dark matter plus Axion matter all really behave like matter, and that can be solved analytically here. And then we get approximately the lifespan to be about 30 billion years. Okay, this is approximate model, but give you a good estimate what it is. If you do it more accurately, more carefully, then you run the computer and you find that what happened is that the Axion energy density will evolve, while A, which is the most important, is the cosmic scale factor, size of universe, if you want, which will, today is 1 by definition, and then you will increase a little bit and then drop to 0. Okay, so what means that the size of universe today will continue to expand until the Hubble parameter becomes 0, and then what happens is that it starts collapsing. The whole universe stops collapsing, and then collapse to a crunch. Okay, that people call crunch a point, and that's the end of the universe. And we can estimate that lifetime will be 33.3 billion years. Okay, so that means that gives an idea that the universe, if the cosmos constant is negative, even though the dark energy we measure is positive, eventually will go to 0 and go negative, and then universe will end in a crunch. Okay, so this is the best value we have from fitting the data. And this gives us a little picture what's going on. Depends on the mass of the Axion field. Isn't that sensitive. And omega lambda. So omega lambda is negative. There's minus 0.6 here. And then this is the mean value, means that instead of taking the best fit value to the data, we take the mean value. And still, this would be like 40 billion years. Okay, so it's not that different. 33 billion years, 40 billion years. And that's roughly the range that will be if the data that W is not equals -1 is correct. So what can we say? Well, it's hard to say too much at this moment, but one can make some remarks. String theories, many string theorists think that our universe should not be at a positive cosmological constant. In fact, it's hard to construct a solution positive cosmological constant. Many would like to have a negative cosmological constant. It's our ground state for the universe. However, earlier, when we know the cosmological constant positive, people find it a little bit difficult to realize within the simple versions of string theory. Now what it says that, well, it actually is negative, okay? So it's quite compatible with the sort of philosophical way of thinking about what string theory can produce. Now, if the vacuum is supersymmetric, then we know the cosmological constant must be negative, okay? That's well known. Zero's unlikely, but not totally well, but generically it's negative. However, a supersymmetric vacuum means the superpartners and our standard model particles have the same mass. Like the electron will have the same mass as its partner scalar electron, okay? And photon will be same energy, which massless for the photino, for example. But we know that's not true. All the superpartners are heavy if they exist, because we haven't seen any of those, no hint. So that means supersymmetry is broken today, which is totally compatible because the vacuum energy here today, the dark energy is positive, means it must be broken. But eventually it can evolve to non-broken. But the key is that if supersymmetry is broken, typically you expect the superpartner split the masses from its partner. But the problem is that the particle we know, the electron, the quarks, the nucleons, their masses are dictated by known Big Bang nucleosynthesis and cosmological background. So the electron mass, nucleon mass cannot be shifted by more than a few percent. So the only way is the superpartners can lift very heavy, but the standard model particle is not changed in early universe. And that's not easy to arrange, but presumably can be arranged, and that will put a constraint on model building if you believe that ground state of our universe is supersymmetric. So another possibility, for example, we already see the equation, the solution is sinusoidal. No, I'm not going to go back, but sinusoidal is cyclic. So if you look at the equation solution, it's very much like this is cosmic scale factor go up and collapse. But once it collapses, it can go to the next cycle. Can it go to the next cycle? We don't know. Classically, it cannot, because the whole thing about collapse, crunch is a purely classical phenomenon. And quantum effect may come into play. Quantum effect may very change this. It's a possibility that we don't know. Okay? That's entirely possible. But that really require a whole new study. But I should mention that even if this can happen, going back, it's not resurrection. It's not, because this universe is very different from this one. And so this, you can think of like if happened, it will be reincarnation. So finally, now we know that there are three types of singularity that we encounter in study of gravity, okay? Black holes, the origin of the universe, we know from inflation, and before inflation, we don't know what it is, but it's really a singularity or something like a singularity, at least classically. And the crunch at the end of university. Now, the end of universe also everything collapsing to a point, so that's a singularity. And the question is, these singularities, of course, have to be really studied more than before. It's possible that at the universe collapsing, the matter get pushed together to form a giant black hole. And then the crunch singularity would be inside the black hole, presumably. And so that may shield or hide the crunch singularity. And that's a possibility. So there's many things we can explore to see what's going to happen. But most important, I would say, is to wait for the data, more data come in. Okay? So let me summarize. The determination of the lifespan of the universe depends on the recent observation that equational state is bigger than -1 and varies over time. And that can be fitted by the Axion dark energy model. It is obviously the observation have to be confirmed and this model have to be checked. Fortunately, number of projects coming along by Dairy Group at different places, different approach, and they will provide different perspective to this dark energy question. So hopefully the lifespan universe will give a better precision determination in the near future. So thank you. Question, Rick? Yeah, I think people can hear you.
Does your model have anything to say about the cosmic tensions,
The Hubble tension.
Hubble and sigma rays?
Yeah, so this is one thing that make us not entirely certain that the data is good, is that when you do the Axion dark energy model, the Hubble tension is not relaxed. Okay, so that means to solve the Hubble tension, you have to find some other way to resolve it. So before the Hubble tension is resolved, we still have some question about the whole approach. But the Hubble tension, on the other hand, the Hubble tension is about 4 sigma, depending on who you talk to. The difference measured, the local measurement versus distance measurement. And it doesn't impact much on the cosmological constant quantity. And so if it's negative, like the best fit value, change a little bit, it will still collapse, except the collapse time lifespan may be a little bit different. So, but still, it's very important to understand the Hubble tension before we say that we really understand what's going on. So,
thank you.
Hello, you say that when W is over -1, then it will then the density will go down, right?
oh, yeah. So the go back to okay. So the equation for CPL model, which it suggests that if you fit the data there, and you will go like here. Okay. So W is less than -1. And so remember what W is. W is the pressure over the energy density, okay? So in order to be less than -1, that means the kinetic term in the pressure must be negative, which implies the simplest explanation is that kinetic energy is negative. And that typical quantum field theory model will not give you that. And so people say that that's phantom causing, means, you know, hard to find a model that's credible.
Yeah, but you say that the universe will have its ended as a new black hole, right?
Maybe this is speculation. We know it's going to crunch.
Then the density will be infinity.
Well, yes. So if there's no black hole, you need matter, all right? It's matter to drive you to the crunch, okay? So matter will clump, okay? It doesn't, so suppose it's just clump together, but it's gonna come more and more because the whole universe, all the matter will come to a point. Obviously, you know, most likely forming some black hole, okay? Now, what happened to the black hole? Well, I don't know. Maybe it stopped the A go to smaller than horizon. That remains to be seen. But certainly, the universe that we know today will end. Okay, so this is an open question. So in that sense, this that the crunch is hidden, but we don't know. It's really remain to be seen. Now, suppose I say, can I consider a universe with no matter? A universe with no matter, only cosmological constant would be negative, and I don't know how to solve the equation, because the Hubble parameter would be imaginary, and then that causes other problems. And again, there's speculations about this from, I don't know, go all the way to Wheeler about there's some fluctuation called geons, something like that, but it's not well explored. But with the cosmological constant plus matter density, then we can classically follow its evolution to the end. That's what we can do. But quantum effect come in at a certain stage, and we don't know how. So that remains to be explored. Sorry.
Professor, can you remark the possible physical origin for introducing this axiom from particle physics or string theory perspective?
In string theory, there's many such axionic fields. Okay, anytime you compactify, you find that this axion-like field, which we really call, how we say, pseudo-scalars in fields, and typically quite a few. Now, depend how you compactify in Calabi-Yau or whatever F theory, you can get dozens or hundreds of those fields. So it's very likely to be there. And then they probably have a mass distribution. And we don't know what that distribution is. So what we do is that we introduce the ultralight ones to try to solve some problem that we face in cosmology or astrophysics. This is one example. There's other ones introduced, for example, fuzzy dark matter have introduced an axion which is heavier, but still 10 to the minus 22 eV. This one is 10 to the minus 32 eV, really, really light. So introducing axion is, from string theory perspective, is quite natural. It's crucial because why they're so light, okay? So think about U1. Okay, U1 has like a Higgs boson, but simple one. There's a phase, right? And the phase, is massless, but in some cases, there's a non-perturbative instanton tunneling, which give it little mass. Okay. Now, if it's not a pseudoscalar, then nothing protects the mass not to be GeV or bigger. Okay. But here we must talk about 10 to the minus 33 eV. Okay. How to protect the mass to be so small, and then pseudoscalar, this angular phase will have that kind of behavior. That's why people want to introduce this axion-like particle, because they have the property which will allow a very small mass not to be corrected. So that's why people introduce that. And in string theory, there are many of those. And in field theory, you can introduce by hand. Yes. That's the question we don't know. So I'll show you the simplest model we have. Here, okay, is that if the whole theory has only matter, which drops like 1 over a cubed, and a cosmological constant, then this can be solved analytically, and A behave like this, okay? And from this analytical solution, we can calculate lifetime, which is roughly 31 billion years old. Now, in real life, that's not what it is, but this can be the case. Now, notice this is sine. Okay, sine can be periodic. Okay, so that's the question we have. It's, anytime it's sine, it can be periodic. However, in the actual case, it's not sine, more complicated, but still periodic cycle. Okay, so you see that here you have the behavior A, which goes drop. Okay, we did go to 0, and then next cycle. Okay, but can you enter a next cycle? That's a question. Okay. It's not clear. We believe classically we don't see it cannot. Okay, but quantum effect may allow it to enter next cycle. Okay, and then this behavior will probably be very different from this. So it's not like something called cyclic universe. People want to do that. Say there's many cycles. We are in one of the cycles. Okay. Because next cycle will be very different behavior than this. So I said, even if that happened, it's not the lifespan of our universe is over. It's just, that's how you use the reincarnation word. Okay, but we don't know. Okay, so certainly it won't be like us. So what we can calculate this one lifespan, I think is the correct way to interpret what's going on. So